Alright, welcome to another draft physics or draft science presentation. The mechanical universe. So we're only up to episode 29. Frankly, this one's got everything in it. So I want to play the whole thing. There's some little dead bits, but whatever. There'll be something to talk about. But really gets to everything that matters in terms of just recognizing how close they were to the truth, and how it was right there to be grabbed, and they just didn't grab it, for whatever reason. And beyond. So again, this whole implication that it isn't mechanical, and yet they're going to talk about how these great scientists were basically pointing out, yeah, it's mechanical, and they've, changed it into something very unmechanical, unsimple. So the electric field, it's really about all the fields, the whole idea of what a field is, when you really look at it, because they make the comparisons between gravity and electricity and then gravity and magnetism. So it's all right there to be grabbed, and it just wasn't grabbed.
In the game of ice hockey, scoring 3 goals in one game is called a hat trick. I'd like to try to pull off a kind of hat trick today. I'd like to tell you what an electric field is.
So again, they don't come anywhere close to tell you what it is. They just don't. Okay, so, they just use, especially now, just jargon. And there's they use the word field, but they don't explain field of what. That doesn't come into the conversation. So they won't be explaining what it is. And what it does, in a sense, is so simple, and yet they make it seem like it's complicated.
Solve a problem in field theory that Isaac Newton seems to have had a great deal of trouble with.
So again, that's just his jargon saying that, it took Newton a long time to prove the inverse square law. Yeah, that's because he didn't have a Hubble telescope, and he didn't have a lot of other stuff. So yeah, it took him a long time to prove it using what data they had available, and making a mathematical proof that the inverse square law. But it's the simplest mechanism. It's so simple. The inverse square law, the thing that it's a byproduct of, is so simple. Again, you create the inverse square law. If I make a universe and just put a bunch of BBs in it, and I give them all a constant speed, and I just put them in a box so they're constantly in the box, and they're always moving the same speed, and I put 2 anything else's in there, anything bigger than a BB, that world will cause those 2 things to bang right into each other if you put them far enough away from the walls. Obviously, you put them near the wall, they'll crash right into the walls, because the walls will end up having gravity. But I mean, it'll illustrate gravity perfectly by the inverse square law. And so that's how simple the inverse square law is.
And introduce an important mathematical idea known as Gauss's law. All of that.
Now, and all Gauss's law says is, if I had a light bulb, right, and I put it inside a box, and I can make the box this big or this big or this big, the same amount of light, total amount of light, photons, are going to hit the surface of the box. So no matter how big I make the box, I can't reduce how much light is in the box. Okay, the photon is going to hit the outside of the box, the interior of the box somewhere, and the total amount of energy is going to be there. And that's what you're going to get in terms of the total amount of light. Now, obviously, the more surface you spread it on, the more diffuse it is. But as light, it's going to be the same. So if I put another diffuser around the light bulb, it's still going to be making the same amount of light. If there's no losses. So I can make the light bulb bigger, and I'm not going to change anything. I can make it bigger. I'm not going to change anything, as long as it's inside the box. So that's all Gauss's law is saying, is that whatever you capture, you capture. So if you make just a ring around something, well, whatever's going on that ring, no matter how big you make the ring, it's going to be the same amount. Because whatever was heading for the ring is still going to hit the ring, technically. obviously you have to make the ring bigger as you go bigger, thicker as you go bigger. But I'm just all it's really doing is just accounting about how much of the light you're capturing. So if you always think about any one of these fields as being a field of photons of light from a light bulb, you'll be illustrating exactly how people like Faraday saw it. That's exactly how they saw it. And if you see it that way, you'll understand it so much better than if you just listen to what they say. Because they don't say it that way. They don't explain it as simply as it is. So Gauss's law sounds, when you look at it mathematically, it looks complicated. But all it's really saying is it's the inverse square law. And you can capture, how much you capture is just a matter of surface. How much surface do you have, and how much surface can capture the energy that's coming off that light bulb. Based on the fact that the light is diverging in the two directions. That's the inverse square law. The inverse square law is light as it travels distance, it spreads this way and it spreads this way. That's the inverse square law. That's the square.
That will turn out to be easier than it sounds because it all flows from the vivid imagination of a great genius named Michael Faraday.
So again, he says vivid imagination, and really this isn't a case of vivid imagination. This isn't Alice in Wonderland. This is like the opposite of vivid imagination. It's confined imagination. It's forcing your imagination to stay within the rules that makes it possible to see it.
Faraday's
almost forcing your imagination to say, keep it simple, stupid. So as soon as your imagination starts making it complicated, your imagination says, no. Make it as simple as possible. Make things move as little as possible. Make everything as simple as possible. Keep it simple. Keep it simple. Keep it simple. And if you keep doing that with your imagination, then you'll stay on the rails. And then you'll get to the truth. Because that's how the universe works. It keeps it simple, stupid.
Life would have embarrassed the most shameless novelist. He began in the most modest circumstances, and he had very...
Well, he was hardly... everything is hyperbole. Everything is just so overstated. Yeah, he didn't come from an elitist, rich guy, bullshit family. So yeah, he had a little bit tough, but it wasn't like he had polio or something. It's not like his struggle was the most incredibly arduous ascent ever accomplished. No. It's sort of like somebody, delivering the New York Times and then eventually owning the New York Times. Yes, it's kind of a wonderful story, but it's not exactly Dickens-esque horror.
Very little formal education, and he eventually wound up being apprenticed to become a bookbinder. But he was intent on self-improvement, and he started attending public scientific lectures at the Royal Institution in London. And he was so enthralled by those lectures that he begged for the chance to do the most menial kind of work at the Royal Institution.
And nobody does that anymore, so that's another part where science just said, forget it, we don't care, we're just capitalists, we want to take advantage, we want to exploit. There's just they have no desire to create any institution where they actually, might fact check each other and make sure something's on the level. Nah, who cares?
And he did begin there, and he eventually wound up as the professor of the Royal Institution and the most famous scientist in all of Europe. Throughout his career, Faraday understood mathematics so poorly that he couldn't read the scientific papers of his own competitors. And yet he had an intuition that got him to the core of every scientific problem.
So again, they blame it on intuition. And when they could say, well, but he had a basic common sense that could see past all that gibberish and just get to the point. What's the point? What's the thing actually doing? What's your silly equation over here? What does it actually mean? There's a relationship between what thing and what thing and what thing. Okay, let's just understand the relationship between these three things without all this gibberish.
It is one of the greatest ideas that flowed from that intuition that we want to speak about today. It's the idea of lines of constant electric force.
There we go. The idea of constant lines of force. So let's not just say electric, let's say magnetic, gravitational. They all work exactly the same way. There's these lines of force that seem to be coming off of things. Now gravity makes it simple because it only does the one thing, attraction. And so it gets a little more complicated with charges and magnetism. But the clear thing with magnetism is, yes, magnetism has the charge elements, obviously the north-south part, okay? And what's the big difference? Well, they're always smashed right next to each other. So magnetism is always in this dipole form, where charge is in this, not a dipole, separate, not smashed together. And that's really the only difference between the two things. And all of them represent, as he stated, lines of force. That means it's all rays, like light. So you have to think about it always is if they say there's a force somewhere, there's flux, there's some kind of thing happening, you have to think about it as, oh, they're rays. Well, where do the rays come from? Well, we know, okay, that with magnets, obviously the rays are constantly being produced. And the magnet never does anything, doesn't get hot, doesn't burn anything, the atoms don't change, nothing changes, so the energy can't be coming from inside the magnet. So it obviously, maybe this force is a reflection. Maybe this is the light's coming from the outside, and you're talking about a chrome little ball, and you're saying, what does the chrome little ball do? Well, it's shining a bunch of light. Well, why? Because the light's hitting it. And so it's just that simple. The whole answer to all of these questions is that simple. The force doesn't come from the inside out. The force comes from the outside, and the thing either transmits it, very seldom absorbs it. The magnets aren't absorbing the force, right? They're not doing anything, absorption-wise. They're not gaining any mass. They're not getting hot. They're not doing anything indicating they've absorbed any of the energy. So the energy is either passing through them, that is, it's being diverted, or it's passing through, or it's reflecting. And that's the choices. And the only thing about magnetism and electricity that makes a difference is, well, somehow these rays of light can either be attracting or repelling. And if they just understood that, well, that's because the force has two types, north, south, plus, minus. So the force is also polarized. Once you have two forces, then you can completely understand. One, the proton reflects the red, the electron reflects the blue. Then you have all the answers, the whole thing's complete, you're done. You've answered all the questions. That's how close they were to the right answer. They were that frickin' close, and they threw it away for this mushy idea of wobbling things and waving things and silly nonsense.
Radiating everywhere throughout space.
So you heard him say it. I mean, that's what Faraday said. He's the king of this stuff. He's the guy who opened all the doors for you, and he just didn't open it all the way. He just didn't think of that extra gimmick that all I have to do is make the force also polarized. So there's protons and electrons, there's proton force and electron force. There, I've now got the tools to answer all the questions. He was that frickin' close.
In the field of physics, surely no tool has dug up more scientific truth than the sharp spade of mathematics.
So another thing, mathematics is describing effects. Mathematics doesn't dig anything. It hasn't revealed anything. It merely formalizes, effects. The relationship between variables and outcomes. That's all it does. It's a formalization of a few variables and an outcome. It doesn't reveal anything. So this is just such a, I don't know why they became, well, they're math whores because that's very elitist. It has this very elitist quality where they know what a lambda means, and they know what a delta means, and they have all their little symbols, and they can play their little game. So this is just some little game, little math whores play with it themselves and say how, oh, aren't we great because we understand what all these silly symbols mean. But it doesn't open all the doors. It doesn't do any of this stuff. It is just such a lie to say that mathematics cleans the window and removes the fog. No, it doesn't. You have to see it to mathematically render it. You have to actually see the effect before you can mathematically render the effect.
Yet when he uncovered the field theory, the groundwork from which much of modern physics grows,
the field theory, and the field theory is really the ray theory. It's light. It's rays of force. So he should have said, instead of lines of force, he should have said rays of force. That's what Maxwell drew. That's what Faraday drew. Okay, and they're not going to show those drawings, but it's part of the story. And instead of saying lines of force, they should have said rays of force that create lines of pressure. So instead of saying lines of force, they should have said lines of pressure. So they should have had lines of force, the rays, okay, they give you an amount of pressure at locations. They're the facts that create your topographical image that you can draw.
mathematics was a tool that Michael Faraday had to work without. But he was exposed to one idea.
Well, I'm sure he could do some mathematics. So again, I think they're overstating his lack of facility or whatever. But you know, you don't need the, again, mathematics doesn't do causes. Mathematics does effects.
That was essentially mathematical in nature.
And look, all the mathematics, most of it, 70% of mathematics is algebra and geometry. It's just dealing with shapes and how they function in 3 dimensions, and again, against a formalization. So it's almost mathematics that can be drawn. You can draw the mathematics, most of it.
In 1789, Charles Augustin Coulomb confirmed what the scientific community had suspected for years. Coulomb finally demonstrated that the electric force is inversely proportional to the square of the distance between...
Right. So he has this extra crap in here indicating that you have to do an integral of some kind. But anyway, but this is the only part that matters, the r squared part. Okay, that's the same radial force. That means it's diverging in 2 directions. Okay, the rays. So the further away you go, the fewer rays hit you, you know, by this square rule. Okay, and so it ends up being 4 times the distance. So the same effect that happens to this hand, I move it twice as close. This hand, to see what size it is, I move it half the distance. It's 4 times bigger than what it was. See, it was this little thing over here before. Now it's this thing, 4 times bigger. Same exact effect, and just has to do with the fact that the light is moving in 2 different directions. It's spreading. So the rays come out, and they're not perfectly parallel. So they come out and they just slightly diverge, but they're diverging essentially in 2 directions. They're not only diverging this way, they're diverging this way. So that makes that bigger square of where they might end up hitting.
Read the charges. As elegant as Coulomb's experiment was, the concept, the idea of the inverse square relation, had been a major scientific notion for some time.
Let's understand the simplest way to create it. So the simplest way to create the inverse square law, the simple mechanical way to create it, isn't to have something in the core of everything that's shooting out, but to have energy coming from the outside evenly in all directions. That creates the inverse square law, every single location in space. If I just create that box of BBs that are bouncing in all random directions, no matter where I place something in that box, it will appear from the thing's perspective that it's getting hit with an equal amount from all directions, which is the same as being a light bulb. It would be like the light bulb in reverse. If you just take the rays and put them all back in, it does exactly the same thing. So the simplest way to make the inverse square law is just to have a random force from the exterior pushing in. And it will also always create spherical symmetry. That is, it will obligate something if it's going to grow. If it's going to collect little bits, it'll collect them spherically. So it explains both why planets are round, why the sun is round, why galaxies are round, why everything's round, and it also explains where the force comes from, where the fields come from.
A century earlier, in fact, Isaac Newton's theory stated that the fall of an apple and the orbit of the moon were both consequences of the same basic laws. And what?
Both perfectly consistent, parachute jumper, all consistent, all right, with exactly what would happen if it's an exterior force.
One of those laws, the law of universal gravitation.
A push universe. So it's the same equation as we just saw before, except the m's are now, we don't have q's, we have m's. So it's exactly the same as Gauss's equation, and all you do is change the constants. You don't even need this part, the little hat thing. That's for, I can't remember what you call that. It's a simple thing, but it has to do with, yeah, whatever, one of their mathematical tricks. But again, it's just this simple rules. Now they're going to say something here that's actually a little bit wrong, but I'll let them say it, and then we'll get to it.
States that any two masses attract each other with a force inversely proportional to the square of the distance between them.
So again, if they would have just say, well, it just means that the force, okay, spreads in 2 dimensions as it travels. The force is, the rays of the force are spread in 2 dimensions, creating a square. Okay, that's it. That's your answer.
But this was a difficult law to apply, even for Isaac Newton himself.
So it's so, in my opinion, is so obvious. So, and again, it's so obvious when you do the thought experiment of the energy coming from all directions and how every single point in space would be thinking that everybody's aiming right at me. All the arrows that hit me seem to be going right for me from all kinds of directions, and they all go right to me, right to my core. That's what it'll always look like.
So, to make the point, he'd have to show that when an object's attracted to the Earth, it acts as if all of the Earth's mass were concentrated at the center.
Yes, which is a terrible way to say it. But I mean, but the point is that everything is a point in space, and if you're spherical, as gravity is going to force you to be anyway, as the obvious answer is, why is it spherical? Well, it didn't come from the inside out spherical. It's spherical because the force is coming from the outside in. That's why it's spherical. It's not because there's a little kernel of round in the center of gravity. No, it's because the randomness of the exterior forces it to be a circle. Quite obviously. I mean, it's the obvious right answer.
And more difficult, he'd have to rationalize what he called action at a distance, a phrase meaning that such bodies as the Earth and the Sun.
Right, so they're talking about things as if we have completed that story and we have answered the question, when our answers are completely vacuous in terms of the modern physics does not answer any of these issues. Their answers are action at a distance. They give you for gravity bent geometry, which means nothing. There's no mechanism. Somehow our little tiny matter bits can see lines that they're supposed to follow. Just nonsense. There's no force involved. Nothing's pushed, nothing's pulled, nothing's anything. Then for magnetism and electricity, use this term virtual photon, has absolutely no definition, just an ambiguous pile of nothing, because they can't give it any texture or reality, because they can't explain why, well, 1 minute it tells you to move forward and 1 minute it tells you to move backward. And they can't explain that, so they have to just leave it, well, we'll just call it a virtual photon. They can't explain where it comes from, because they know the magnet's not burning any energy to produce magnetism, so they have absolutely no explanation for where it comes from. They're still stuck with spooky action all over the place. And they're talking as if they've fixed that. They haven't fixed it at all.
Apply forces directly to each other, even though they're separated by millions of kilometers, with no tangible connection between them.
No tangible connection except the obvious one, that it takes time for the force to get there. So obviously it's not completely spooky action, because you say, well, complete spooky action would be instantaneous. So Newton couldn't know that. They didn't really know the speed of light yet in any real way. But I don't know how. I don't know how much they confirmed it even in Benjamin Franklin's time. I don't know if they could really say for sure. But anyway, the point is once we know it for sure. Okay, we know that it takes time, that these things are moving. This force is moving the same speed as light. So once Maxwell did his work, we know it's the speed of light. All these forces are moving exactly the same speed. I mean, that should just be a huge giveaway. Oh, we don't have to have spooky action, because obviously the action takes time. And why does it take time? Oh, because it's a real thing that has to go from point A to point B. A real thing has to actually travel to the destination. So when they say virtual photon, they're saying it for that reason, because they know it's going the speed of light. So that's why they blamed a virtual photon, some kind of magic photon that creates attraction and repulsion. And the reason why they can't put any definition on that is because they didn't have the imagination to say, what if the force has two charges, plus and minus? There. Now you can explain attraction and repulsion. High pressure, reflections. Low pressure, no reflections. It's that simple.
Though the great genius was often a bit testy, even he himself might have come to admit a certain dissatisfaction with the idea of action at a distance.
So I don't even know why they even said all of that crap. They should have just pointed out that, yes, Newton found it troublesome that he couldn't provide an answer, and he was honest in stating that he couldn't provide one. He can't even pretend to have an answer, because he has no answer. And instead of just saying that overtly, they say this rubbish.
Perhaps somewhat defensively. In the Principia, Newton wrote,
so why add this somewhat defensively? It's not a defense. He's just admitting a truth.
I have not been able to discover the cause of those properties of gravity, and I feign no hypothesis.
Right. So he doesn't pretend to know the answer. He's not going to sit there and just, well, here, I'll put in this book a bunch of gobbledygook about what I can possibly imagine, like angels are pushing things or something. I don't know. So yeah, he didn't put some jerky, stupid explanation he just made up that has no credibility. He just said, I don't got one.
That famous phrase, I feign no hypothesis, Newton felt no obligation to explain.
But he had plenty of interest in the subject, so let's just not pretend he just said, well, forget it, I'm not going to think about it. He thought about it a lot. Fadio communicated with Newton. I don't know whether it was before or after the Principia, so I don't know that truth. Newton liked the idea of particle gravity for quite a while, so it was one of the viable explanations. And again, particle gravity doesn't give you charge and electricity, but Newton didn't know anything about that crap yet anyway. But we do. See, that's the thing. We do. We can look at this history and we can see where they made the mistakes, and nobody's doing that. They're seeing the wrong thing as the mistake. They're getting, but all you have to do is backtrack through this, and you can just see where, okay, they had that question. Well, we have the bigger context. We understand electrons, protons. We can understand, oh, well, if the force was also being differential, then those two charged bodies could be differentiating based on the different force, and so one they reflect and one they don't. There, we've solved the problem.
By either physical or mechanical means, the law of gravity. To us, it is enough that gravity does really exist, he added, and act according to the laws which we have explained. Obviously, that was enough.
Well, it was certainly a lot of work to do what he did, so that was good, but, obviously it's not enough. It's enough for the book he was writing. But I stated, there was plenty of indication that Newton found the question in need of an answer.
In England thereafter, the law of gravitation was the law of the land. And by the 19th century, with the law of gravitation firmly established, Newton's...
So again, the law of gravitation, the formalization of the strength or mechanism. That's all. It's just a formalization of what you can expect. If you put certain variables in, this is what you can expect in terms of the amount of energy or force that will be produced. Nothing, this is not the end of the story, okay? It has nothing to do with describing causes again, and causes are so fundamental to understanding how it physically works.
His followers had discovered that electricity and magnetism obey similar laws.
Right, and they have the same speed too. So again, the similar law is just the obvious one, the inverse square law. There's nothing else to the equation except the inverse square law. That's the key ingredient to the whole thing. So yes, they share the fact that they're inverse square. They share the fact that they will create spherical symmetry. That's the tendency. They share lots of facts together. You see, you smash a magnet to pieces, it'll try to go spherical because it's the same force acting on it.
In all of them, the force decreases with the square of the distance.
And they don't point out how they all have the same speed, which is really important. Same speed, and the force has this common. So here they say the magnetic field. Now that's only true when you're using two dipoles. So this becomes an r cubed, depending on what you're using as a test charge. So if your test charge is a monopole, I think how to say this. Well, at any rate, this one changes. Okay, the magnetic field becomes r cubed because the magnetic field is a dipole field, which means the two fields blend into each other, which creates a neutral field.
The similarity is amazing. The question is, why?
I guess what I'm saying is that this is only true when you're put a north-facing magnet to a south-facing magnet. So if you have two bar magnets and you face the north to the south, then you have inverse square. But if you do this or some other version, you'll get a different R number.
Perhaps because the inverse square law is related to a simple geometrical property of three-dimensional space.
Right, that's it. A simple geometrical property of three-dimensional space. And what's the geometry created by? Oh, that's right. An external even force would create all of the geometry.
Space. And perhaps because these forces aren't the only things that diminish with the square of distance.
Light does exactly the same thing. Again, this hand does exactly the same thing. Your image of this hand and the photons from this hand will do exactly the same thing. Because I'm radiating the image by the same effect. The light's reflecting off me is doing exactly the same thing.
The essence of the inverse square law can be seen in the concept of flux, the Latin word meaning flow.
So again, it's this using stupid words to describe something. It's calling the light off a light bulb flux, or the sun, the light coming off the sun flux. Not a great way to understand what it is. It's a bunch of rays.
Light flows out from the sun equally in all directions.
Right, and if you see, and this is a terrible diagram just because there's nothing random about this. It's all clumpy and horrible, and they should put it in ray form just so you get the idea. And all you have to do is invert this scenario. Have the little bits go in and hit and reflect. Right? So you see how easy this is? So have them go in and reflect, and you got exactly the same field going out. All right, now you have an explanation for where the energy came from. Now you know where the energy came from. The energy was already in the universe. All right, and now then just change its color. So say when it's yellow, and just have two different colors of rays coming in, red and yellow, and have all the yellow rays bounce off, reflect, and then have the red rays, let's say, well, they're also going to reflect off a single charge. So again, I have to put more than one charge in the scenario for you to see how it gets changed. But the idea would be a red ray is doing something slightly different. So the yellow one comes in and it reflects straight back, where the red ray, okay, is going to come out perpendicularly, some other direction than what it went in. And that's all the difference there is. That's it. That simple change explains all electric and magnetic functions. It can be explained by that simple idea that one force reflects straight back, the other force leaves in the wrong direction, in a perpendicular direction. And you've done it. You've completed. You've now got all the elements to explain all the phenomenon we observe.
As it spreads out, getting farther from the sun, its intensity decreases.
Right, and it's all that's saying is, well, up here, in here, you're likely to get hit by one of these little things really easy. If I'm this little circle here, I'm going to get hit all the time. Well, that's the wrong way to do it. If I'm this little arc, this little line. And then you can see that these two dots, when they were right here, were right next to each other, so my little line would hit them. But if my little line's out here, both of them will miss. So obviously, with distance, you're and again, this is a two-dimensional thing, so you're not getting the idea that these things are separating from each other, not only on that flat way, this way, they're also separating from each other this way, depth way. And that's the square.
But imagine a sphere enclosing the sun. All the light would pass through the sphere, no matter what its distance from the sun.
Right, so it's all the same number, but obviously they're spread over a larger area. But from the perspective of a viewer, you wouldn't see any difference between this sun radiating the spread light versus the little tiny one radiating light from a lot more, in the sense based on its surface area. But the view wouldn't change out here. It's not going to change how much photons get out at a distance.
And the area of the sphere grows as the square of its radius.
So this is just another way of doing the inverse square law. So it's just basically saying, as you make a circle, as you increase the diameter, you increase the circumference, the area of the sphere by 4. So it's just telling you basically the same. It's the same square law. The square law, in my opinion, is enough explanation. But the circle duplicates the same proportions. In terms of, you increase the diameter this much, you increase this area 4 times.
So the amount of light energy per unit area decreases as the square of the distance.
The inverse square law wasn't the only provocative idea to which...
And the really important part is to understand that the inverse square law, again, is pushing everything from the outside in. So everything is, and when it's inside something, that's why the whole mass thing is what's creating what's blocking the force, what's absorbing the force. So whatever absorbs the force means there's no force getting to that location, which means the thing moves into it. And that's why everything gets compacted.
Faraday was exposed as a young man. By 1810...
if the force was coming from the inside out, you could sort of imagine that would mean all the little bits would want to fly off, not collect. Another intuitive, another common sense, reasonable reason not to go with an internal force pushing out and think of an external force pushing in is the mere fact that why do things become solid? Why do they clump? Well, they clump because the force is moving in that direction, from the outside in, not from the inside out.
He was a regular visitor at the Royal Institution, particularly at the lectures of the institution's legendary professor, Sir Humphrey Davy. Chemist and natural philosopher, a scholar who was knighted, made a baronet and president of the Royal Society. Davy was the very crest of British science. With his own research.
So, the sort of interesting part is that Faraday really started as a chemist. So his real initial obsession was chemistry.
Research as the subject. Davy spoke as the world's authority on every element from sodium to potassium, chlorine to iodine. Davy became a scientific father figure for Faraday and remained a mentor and enormous influence for almost 20 years, although the relationship was at times a rocky one.
Yeah, well, I think the guy sort of exploited him, frankly. That's the rocky part. Gave Faraday all the grunt work and, he took all the credit.
But under Davy's influence, in the golden age of chemistry, none shone brighter than Michael Faraday. He discovered benzene, liquefied chlorine gas, and developed new alloys of steel. The list of his remarkable accomplishments as a chemist goes on and on. Nonetheless, in 1821, Faraday set aside his work in chemistry. In that year, Oersted discovered the effect electric current has on magnets. And while that effect can be seen clearly now, in 1821, it was still a great scientific mystery. Indeed, why would the compass needle line up perpendicular to the electric current?
Yes, why indeed. Well, no point going into all that.
Sparked by curiosity to begin with, and asked by an editor to write an article that would end the scientific confusion, Faraday set out to solve the mystery for himself.
So they always talk as if, he set out to solve a mystery as if he solved it. He didn't really do that. So again, it's just, no, these questions really hadn't been answered. And that's why you're still stuck talking about virtual photons. It's because you don't have an answer.
Faraday saw the possibility of harnessing the force of an electrical current and invented a device to do it. That device happened to be the first electric motor.
See, the really important part of this is the force is the thing pushing on the conductor. That is, pushing it to the outside of the circumference. That's the force that's really powerful. The minor force is the motor force that's causing it to rotate. So the primary mover is the movement out. The weak mover is the fact that there's a bias in a direction. The bias is very weak. The push out is very strong. So all you need is a little bit of bias when you're pushed hard. It's a little bit of bias in this direction will cause your force, the strong force, to do a lot of acting in terms of bending it around. But the strong force is the out force. The very weak force is just that slight little bias that makes your force to have that circular consequence. So the motor force is the thing that makes the motor force work is the repulsion created, the strong radial force that's pushing it out. That's the real source of the force. The real power of it. These are all stuff that they never explain any of this, right?
How did Michael Faraday manage that? Perhaps because, being unable to analyze them mathematically, Faraday was able to take these circular magnetic forces at face value. In any case, to Michael...
Well, yes, and that's what you should do. You should start with just the basics. What does it basically do? And then you compare it to other things, and what do they basically do? And then you find these things in common. The same speed. Oh, the same inverse square law. Oh, these are probably caused by the same thing. Well, none of these things, the Earth doesn't seem to be burning any energy to create gravity. So where's the gravity coming from? Where's the force come? Oh, it must come from the outside. They were so close. Just let it all... Again, Fadio 350 years ago, the guy came up with this particle gravity theory. If they would have stuck with that, then they would have saw that, all we have to do is give these little particles plus and minus character, make them blue and black or red and green or some kind of color difference, and then we can answer all these questions. So close.
Faraday, electricity, as well as magnetism, apply real forces in space.
There we go. See, that's it. So I love this Faraday guy for that, okay? Yeah, the real forces, not fake things, not bullshit. It's real stuff, pushing stuff.
And he began his study of them with a number of assumptions.
And they're not assumptions, they're deductions. So again, I just hate the way they say this stuff. He didn't just assume something. He deduced that it probably has to be that way. So he said, okay, what can I deduce as facts? Again, where do the facts point? He let the facts point to the truth.
Anywhere in the vicinity of an electric charge, a small test charge experiences a force.
Now, see, this is the important part to think about, okay? So he did this vector is describing the strength of the force. And so what you're basically doing is say, when they say lines of force, what you'd say is where does this line stay the same length? And all the places that line is the same length, well, that what you draw as a line of force. But what's really causing it is this radial crap. It's radiating the force at the inverse square law, just like gravity or anything else, and you just change the direction of the arrow. So gravity is doing exactly the same as this test charge, just point the arrow in the opposite direction, and it'll do exactly the same thing.
If it's due to only...
See, you move it close, it pushes it far away. See, it's the red and red. See, they're just so close to getting it, you know. And so this is basically an electron and an electron, it would have to be. I mean, you know, to really have this clear an effect. But you can see, when he brings it close, it gets stronger, the repulsion. Bring it further away, the repulsion gets weaker and weaker. Inverse square law. But exactly, like I said, just reverse the arrow and you have gravity.
Only one charge, the pattern of forces detected by the test charge is simple.
And what is it tracing out? It's tracing out an obvious lines of force coming from the object, obviously. That's what they mean by lines of force. So when they do this other stuff, that's not lines of force, that's lines of pressure. That's showing you how much pressure there is at that location. So like a topographical map, it's explaining to you what the elevation is, where all the elevations are the same. It's drawing a line where they're all the same, but it's not explaining to you what causes elevation. The force, what's the force? The force, as Faraday is saying, is this radial force, like sunlight. So think of this thing as being light, and how much light is hitting the object. And that's what it's showing you. The bigger the arrow means more light's hitting the object. Yeah, that's a simple, again, it always comes down to that. You want to understand it, always just think about it as light radiating. How much light is hitting it? Well, the closer I go, the more light hits it. The further away I go, the less light hits it. It's a straight line force.
The pattern's more complex for two opposite charges.
Right, so then you're changing to attraction. So you have to kind of understand that the red is reflecting off this little red thing. So when the red is close, there's lots of reflections between back and forth, because the red reflects, red reflects, red reflects, red reflects, red reflects. So it keeps reflecting, creating more pressure. But as it gets further away, the reflections slow down. There's less reflections, being, less, and less. And the point is between this red and this blue one, well, all the blue stuff is flying out this perpendicularly here. You don't see it, but all the blue is flying out. So none can reflect back and forth here. And all the red force that's hitting this blue thing, no, it's coming out this way, and this way, and this way, and this way. It's coming out the other tangential or perpendicular dimensions. So there's no red force bouncing back and forth. So the exterior force is now much stronger on both these objects, moving them towards each other because there's no force pushing them apart. They're shadowed the force. And theoretically, as they move towards each other, they will increase, okay, the effect, because they will start absorbing force. That means the red force that hits this one will get absorbed by this object, and it'll never hit this one. So now these are lines indicating which way it would move, okay? If you put it in that location, what would be the combined effect? This repulsion plus this much attraction. So the attraction is kind of weak here, Repulsion is strong here, so you end up with a net vector in this direction. So it's just telling you after the addition, after this thing gets hit by both forces, what would it do if it had no motion? If it had no velocity, and I just put it there stagnant, I let go of it. So just think of this thing as a neutral, and you let go of it. What would it do? Well, it's not obviously neutral. It's obviously repulsive and attractive. I mean, it's obviously the same charge as the red. And what would it do when you just let go of it? This is the vector of where it would go. It's the vector of where it would go that instant. And every time it moved, the equation would change, and that vector will become a curved line. That's what they'll show next, which is very confusing. But I mean, it's confusing in the sense that they create every opportunity to confuse rather than to enlighten, in the sense that they got to make distinctions between what these things are indicating at any specific moment. Again, this charge will not travel this straight line. It just means at this moment there's this much energy pushing it in this direction. But as it moves closer to this object, this line will change and it will move towards the blue object. So this line will bend.
Or for two
and that's
charges
what you'll
of
see.
the same sign.
I mean, frankly, these illustrations are better than some of the dopey ones they show, because at least they're showing you what the force ends up adding up to at that location. But what they should state that as soon as you change that location, though, this force vector this arrow will change direction, which means that if you want to know the actual path in this circumstance, the path won't be this line, the path will be some other line. I mean, obviously in this direction. It'll start in this direction, but it will probably veer this way. Yeah, because there's a charge here and a charge here. So what's going to happen is it'll start in this direction and veer this way. I mean, you can see that as he moves it, the pointing vector points to a different location. So you can see it's constantly going to change. But it's just telling you how much velocity it'll get this moment, how much velocity. And once it has velocity, then you have to account for the actual velocity it already has in terms of getting its actual path correct. Because its path will have momentum then. So once it has momentum, then its momentum has to be added to the effects of the two forces.
And more complex still, for more complicated arrangements.
So again, these arrows are just at that exact moment, what's the strength of the push? Which way is it getting pushed?
But in any case, here's the point. Even if the test charge isn't there to feel it.
There, this is the important part right here. Bingo. So this is what Faraday's really saying. Radial force, all right, and always there. There's no something has to be in the field. No, the field's always being produced because the energy's always coming from the universe. And it starts with gravity. That's where you first see it. Always is there. Right there. That's that stuff. Same force. Pushing that down because the Earth has absorbed a whole bunch of force going the other way, and there's a bunch of not force here. It's missing. It's a bunch of force missing on this side, and it exists on this side. And that's why this falls. It's because it's being pushed. This is so simple.
The pattern of forces can be imagined to exist everywhere in space. This is the essence of the idea of the field.
And again, all the field between these charged bodies is a reflected field. It's the field reflected. So their apparent energy is not their energy. It's coming from gravity. Oh, leg
And
cramp
although
again.
Faraday only imagined it, the field can also be expressed.
Sorry. Leg cramp again. Ooh. Yeah, just a lot of moving, tearing my life apart, picking it up and throwing it out. It's a lot of work. So eventually they'll turn this into these ciliar lines. And those ciliar lines are lines about projected paths of objects once they're moving.
The force that acts on a test charge at each point in space is equal to the test charge times a quantity due only to the other charges.
So it's just telling you that the charge will add up all the other fields that are affecting it. That is, all the influences, all the changes in the influence. So I'm getting more green from this guy. I'm getting, more red from this guy. I'm getting some green from that guy. And I'm getting more. So it just has to do with a percentage of color. So the blue things are reflecting more blues. The red things are reflecting more reds. So you're getting a different feel from each one. And again, from your perspective, you're either red or you're either blue as a test charge. They don't use neutral test charges because that's essentially a dipole. But anyway, and so they're neutral. You're going to react to the combined total. So if you're red, and it's the net field is saying it's 60% more red than it is blue in this whole dimension, well, then you're going to run from that dimension because there's more red coming at you than blue.
That quantity is the electric field.
So again, it's all the same fields. It's just the field's potential. So this is all one field. It's just one field of force. It's not an electric field and a magnetic field or any of that stuff. It's all the same exact energy.
Faraday never arrived at that definition of the electric field. But by seeing both electric and magnetic phenomena as forces in space.
And let's understand, I would argue that the only reason Faraday didn't do it is because he didn't fall on this simple answer, the simple fix of understanding that it's all one field. And all you have to do is make the field just like protons and electrons, give the field two charges, just like the north side of the magnet and the south side of the magnet, give the field, give the energy, give the photons two types, and then one side, then you can see everything's just a filter. Everything's just filtering what comes in. It either passes it or it reflects it. Huge difference.
He managed to see further than his peers. As a result of this, and many other discoveries, he eventually became director of the research laboratory at the Royal Institution. And succeeding Davy, he became the professor there, as well as a member of the Royal Society. But it was as researcher, rather than instructor, that he saw deeper and deeper into the invisible forces of space.
Right, so they're just basically saying it probably would have been better never let him be a professor because he did much better work when he wasn't a professor, which is true for everybody. Sadly, once you're comfortable, I don't know if I want to do all that work.
To Faraday, the 1/r² force between electric charges.
So again, this is just a horrible representation. So it would be much better if they just showed longer lines and just showed them like a sunlight, just rays of light, rays, spikes. This blobby, whatever it is just not a very good representation of the evenness of the force.
Suggested that the force must be applied by something radiating outward from charges.
Then again, the only thing he's missing there is, oh yeah, it doesn't radiate out, it reflects. So as long as it's a simple fix, but it's just so critical. This idea of, yeah, it has to, if there was an external force, you'd have to figure it out, right? You'd have to say, what are the choices? Well, it either reflects off of it, it absorbs it, which means, well, then it has to get hot or has to do something, it has to move, has to do something because it's absorbed a big piece of energy, or it lets it back out somewhere else. But that's all there are, right? There's just reflecting it, diverting it or absorbing it, keeping it. That's all there is.
Something which, like light from the sun, never stops and never ends in space.
Right, gravity's always there. It's elemental in the universe. The cosmic background radiation never stops. So I'm just saying it's the same source, the same mechanism. Whatever's creating the cosmic background radiation, well, that's where gravity's coming from too.
As Faraday imagined it,
There we go. I mean, there's the drawing that matters. There it is. It's showing you exactly this is what really causes the effect. Is straight line forces. Straight lines, not curved lines, not weirdy paths, not any of that crap. Straight lines. That's the only stuff moving. Those straight lines are the only thing moving. Everything else just moves based on how many of those straight lines it gets hit by. It gets hit by one from this direction, one from this direction, one from this direction, one from this direction, and what color they are, of course. But don't forget about color for a moment. We don't need it for this point. But this is what he saw, and this is how close he was to the truth. And all he was missing was the fact that the force comes from the inside out. It reflects, and it reflects based on whether it's red or it's blue. Because it's going to either reflect red or it's going to reflect blue force. And there you have it. You're done. That answers it all. Finished. Physics completed.
this something would be lines or tubes, each one capable of applying a force to any charge in its path.
I mean, there it is, right? So all this wavy crap, all this, dopey line stuff there. Faraday knew it. It's a straight line, dead straight line, force, radial force, rays of force. And all that really means, if you break it down, is a little cannonballs at a distance, or cannonball, cannonball, cannonball. It's shooting cannonballs. Cannonballs hit it, they bounce off, they're kept, which means the thing moves, or they're deflected in some other direction. That's it. Those are the three choices. Nothing more. It's that simple.
These lines of force would begin only on positive charges.
Okay, so now they've done the, let's say, what would happen to something if it left this building? Okay, what happens to the space shuttle if we shoot it off? Where would it go? Well, that's what they're showing here. They're showing what happens when you throw something, a charge. Where does the charge go? What's the path it would take? So that's all this is illustrating, is where would it go? So if you pop a blue off of here, what happens to it? Oh, it gets attracted to the red and it crashes into the red. And if I throw a red off of here, what happens to it? Well, it gets attracted to the blue and gets sucked into the blue. So that's all that's illustrating. If I shoot it out this way, well, then I'm running away a little bit from the red, but I'm still attracted to it, so it starts pulling me and pulling me and pulling me. And really what's happening is the exterior world is pushing it because there's less and less reflections. I mean, less and less, it's attracted to the blue, and it's, oh yeah, it's a blue that came off. So it's repelled by the blue, that's its impetus to leave. So that's what the fuel is that's pushing it, all right? And then it's attracted to the red because the red's absorbing, sending all the blue stuff out sideways. So none of the blue that was coming, that hits this side of the red, none of that blue comes out this end. It all goes out this sideways ends. And so the object here is saying, I'm not getting hit by any blue here. No blue reflections. And so it's getting pulled towards the red. That's all these lines represent, is what's the path of something that you eject. This is an ejection path. This has nothing to do with what the force is doing. The force is radial. So this is where they use lines in three different ways, and they end up just confusing what lines mean.
And end only on negative ones.
See, in theory, you can't create this without, again, you have to shoot red off of here to have it land here on the blue, and you have to shoot blue off of here to have it land on the red. So this isn't something that happens to any real object. No real object travels this path.
they would flow smoothly through space, never crossing or tangling.
So they're just showing you what happens to with the repulsion. It's just kind of obvious, right? I shoot a red thing off of here and it feels the pressure off of here because it's reflecting. So the force reflects, creates reflections. So it's saying I don't like either one of these choices. I'm getting out of here. So it just starts to run the hell away because both of these things are reflecting, creating more pressure, extra pressure. See, I mean, this just doesn't tell anybody. This is just such an unrealistic description. Again, because you have to know ahead of time that this line only means something if you know you're shooting a blue one this way and you're shooting a red one this way. So you have to understand that this path, nothing real takes this path. Except if you make them all red, then these lines are valid. Okay, but they're not valid going the other way.
No matter the configuration, the charges would have a characteristic pattern of lines.
Well, I suppose they are valid the other way if you're shooting a red off of the blue. So if you just make all of the charges one color, make all of these lines representing what happens to, say, electrons, then they're valid in that sense. So if you just make all these lines, see, they should have made the lines. So should have chosen. Well, see, they're using this little test charge over here, red. But there have to be one charge or the other.
The force they applied would be strong near the charges where the lines are crowded together, and weak far from the charges where the lines are.
Yeah, I think they would have been better just to show Maxwell's drawings, because Maxwell's drawings puts the lines on the paper and then puts the rings on the paper. But Maxwell didn't do this three-dimensional thing, so.
Are farther apart. The ability to apply a force resides at each point in space.
So the ability to apply a force relies on each point in space, but again, that just it's implying that space creates the force when no, the force is in the space. Yes, constantly, randomly, coming in all directions. Ugh, this is so annoying.
And the force arises from the intensity of lines.
Yes, and the force arises because there's something changing it. So if there's nothing else in the environment, if you're all alone in space, there are none of these curved lines, okay? Because there's nothing to cause any curves. There's nothing to cause any change in the force. So you just stay where you are, and you have gravity on your surface, and that's it. There's nothing else going to happen at all. And it's not until something else shows up that things start getting interesting. And the something else has to show up if it also is just made of a bunch of magnets in all kinds of different directions. That is, atoms that are where the polarization isn't in one direction, so you're not magnetic, then you're not going to be charged, you're not going to be anything. And so the only effect is going to be gravity. But if the other thing that shows up is red, or the other thing that shows up is blue, well, then things are going to get interesting.
Regardless of the location of the charges that create them. Even without such.
So, I mean, this moving it around in a nothing field is just, see, they're pretending there's some field being created by something that's causing all these crooked lines. And then they're moving it around saying this is somehow space. No, empty space doesn't do this. Okay, this is just a distortion. They didn't do anybody a favor by this animation, because it didn't explain that, oh, obviously there's something over here that's intensely gravitational or intensely charged.
Such space-age graphics. This is how Faraday pictured the electric field.
See, he didn't do it that way, in my opinion. Okay, he didn't. Again, the most important part were the radial lines and the fact that they diverged in the two directions, and that gave you the inverse square law. And then everything else was just measuring the pressure from whatever number of things you put in the field. It changes the pressure. Either there's more reflections or there's no pressure. So it's either high pressure or low pressure. And I think that's how he understood it.
And it still seems the most graphic way to visualize one. But satisfying the scientific community would take another step or two. Necessarily, those steps would be mathematical.
Necessarily, he
And one of the
says.
more important was taken by Carl Friedrich.
You know, to say that it was necessary, it wasn't necessary. It's not necessary to understanding the causes and effects. The mathematics is completely unnecessary to understanding mechanism and mechanisms that are capable of producing the effects. They don't have a mechanism. They have no particle. They have no thing. They have nothing as a mechanism that's causing the energy. And so the next necessary step was to understand a mechanism, to say it's particles, to say it's something, not nothing. That was the next necessary step.
Gauss, physicist, astronomer, and perhaps the best mathematician of all time. Gauss's mathematics would offer an elegant complement to Faraday's.
I think that's just such a bizarre statement, but whatever. I mean, there's lots of great mathematicians, so I don't know how you can do that whole, perhaps the greatest, when he didn't have to do some of the bizarre math of the modern era.
Idea, and it would become law.
So again, this is just the simple thing. This is just saying the simple thing, that if I put a light bulb in a cardboard box, the photons are all going to hit the outside of the box. And it doesn't matter how big I make the box, the same amount of total light will hit the interior of the box. That's all this is saying.
In Faraday's terms, flux is represented by all the lines of force passing through any surface.
Right, so now we're back to lines of force, okay? These are the little bits flying off, reflecting. They're the bits, the energy, okay? Not those stupid, wacky projectile lines, not the lines of where will something go once it's in a field. Not those lines. These are the actual lines of the actual energy, the light. So if you think of it as photons, again, so all you're saying is there's light coming and there's rays of light, and I put a surface in the way. How much light hits the surface? That's all you're saying. That's all this whole thing is. That's all Gauss is doing, is saying, well, if they're this far away, less of those little lines are going to get through the surface. And if it's closer, it's going to get more lines. And if it's a closed surface, a square or a circle or whatever shape I want to make it, it doesn't matter. Because no matter where the photon goes, it's going to hit some part of the surface. So the surface will collect all of the light.
Gauss's law states that for any closed surface, the total flux is proportional to the net electric charge inside.
Right, so he's just saying whatever permeates it is how much charge gets to whatever the surface is. And the bigger the surface is, then you have to divide how many of these little holes you have over the surface area to find out how much actual charge you're going to have on the object. But yeah, it's really not that complicated.
If there's no net charge inside a surface, any positive flux outward through it must be balanced by an equal amount of inward or negative flux.
So just basically saying that if you have an uneven charge, then one side's going to have to, in a sense, create the other side. If you're going to move pressure from one side, it has to leave from the other side. And again, not too hard to figure out. If you're pushing stuff, well, I think you can get that. Can't make something from nothing. The force only pushes stuff. So whatever stuff you got, it'll push your stuff and rearrange it. Well, if it rearranges it and puts more red on one side, well, that means more blue is going to be on the other side just by obvious deduction.
Gauss's law, which gives mathematical definition to Faraday's intuitive notion.
It just takes the basic variables of things. You're saying how much stuff do I have that has charge on it, and how much stuff am I reacting with how much charge on it. So it's just formalizing again the variables that were established. So it's just a formalization of the variables that cause the effect. How big is the substance? How thick is it? How this, how that? And just telling you, giving you an equation so you can figure out something if you need to. But it does not give you any clue what's causing the effect. The mathematics does not explain causes.
About the electric field is actually an expression of the geometric meaning of any inverse squared law. In appropriate form, it applies not only to electric fields.
And again, the inverse square law is really should be seen as what, R should almost stand for randomness. This is what random or equal from all directions. This is what it creates.
But to gravitational and magnetic fields as well. And even to light flowing from the sun. In any event, Gauss's theoretical work, combined with Faraday's common sense, reveals...
Faraday was the one close to the just inches from the truth, just inches from putting it all together.
There's a number of amazing facts about nature itself. For example, watch what happens inside a conductor where a lattice of positive ions is neutralized by mobile and constantly moving electrons.
So there's nothing in this. I don't even know what this simulation is, but it doesn't do anything. And so again, they're talking about the movement of the electrons, and frankly, that hasn't been proven. The electrons go anywhere at all. And the only real fact we know is that pressure moves from one end to the other, voltage. Okay, so the atoms don't have to actually lose electrons. Electrons don't actually have to go anywhere for you to get the same effect. As long as there's electrons, atoms connected to each other, that means there's electron pressure connected to each other. Electrons automatically share their pressure. As soon as another electron shows, I'm sitting here, I'm an electron. I have two other electrons next to me. We've already balanced our pressure because we have to. We don't have any choice. I hate this guy. I hate that guy. If I hate this guy more than I hate that guy, well then I move a little bit away from that guy. We automatically balance our pressure. Automatically. And so as soon as another atom shows up, well, the atom has an electron. I see the electron. That's the thing I see. I also see the proton, but let's not get into that. But I see the electron, okay, and I'm going to balance to that electron's pressure. It's going to balance to my pressure. So again, we're going to balance the pressure. So all that's really happening is the pressure. You give more pressure, you push two electrons too close together at one end, and that I push this say this electron, there's a whole bunch of electrons in a row. I push this one, I just pushed all the others. They're like dominoes, except they don't actually have to move. Their pressure is transferred by a tiny amount of movement. Tiny amount of movement. They exchange a ton of pressure by just moving a little bit. So they exchange the pressure, The electrons don't actually have to go anywhere. All that has to move is the pressure. See, there's nothing in this animation. I don't know what they're showing. Well, the dots that aren't doing anything. Look, watch the electricity move. It's not moving. Maybe he'll do something now. Still not doing anything, right?
An electric field passing through a conductor forces the electrons to flow.
So again, that's nothing that's been proven. It wasn't proven by Faraday. It wasn't proven by Maxwell. It wasn't proven by anybody. So that's just what they're saying. Just like when they say the electrons are spinning around the atom at 400,000 miles an hour or whatever. They're saying so. They really don't have any proof that that's true. None. It's just their theory. And based on, well, we think so. That's all they really have. They just have, well, we think so. That's the image we have in our head, and that's the image we have, and we're sticking with it. Even though it's probably not a really rational image. And you can think about it in so many ways. The electron has to be affected by photons hitting it, and especially at a frequency. The only way it can detect a frequency is somehow that electron's got to get hit by the same energy, the same stream, the same ray. Pieces of it have to hit it. So if it's buzzing all over the place, it's bad enough that the atoms are already jiggling, Brownian motion and heat. It's already moving. But fortunately, that movement isn't faster than the speed of light, so at least it has some chance of hitting the electron. But if the electrons are actually spinning, how could you ever hit an electron? It'd be impossible. I mean, with more than 2 rocks. You throw the first rock, and by the time you're throwing your second rock, the damn thing is gone. How the hell could I hit it again? You couldn't.
Until they pile up at the surface, repelling the motion.
So again, none of that, I think, actually happens. You don't need to have that actually happen. They don't pile up. They get higher pressure. They get closer together. So they don't pile up. They just get closer together. So they're under more pressure. They're more irritated. If they get pushed out a little bit, they'll push out much faster because they're closer together. There's higher pressure. The vector arrow between them is longer because they're closer together and they don't like it. They're under more tension. So they should have just drawn these little dots closer together at the edge and further apart the further away you go. And that would have been a more accurate, I think, way to describe the effect, the cause, the actual mechanism.
Motion of further electrons. But that means the electric field inside any conductor becomes equal to 0 when electrons...
Yeah, well, it goes to 0. That means it neutralizes. That means all the electrons, if there's a change over here, the change will move at the speed of light or close to it, as close as it can, look, it moves the speed of light between the 2 electrons. You can get that part, right? It's moving the speed of light between the 2 electrons. But as I move one of the electrons a little bit, that takes a little bit longer. So it moves a little slower than the speed of light because it has to spend some time moving the electron, which slows it down a little bit. That's why light moves slower in glass. It slows it down a little bit. So it gets slowed down a little bit in a conductor. But the idea is, of course, all the electrons are connected to each other. They're all pressurized the same, and they're all going to say, equalize the pressure. So no matter what you put on it, whatever you hit it with, the ground neutralizes it. So it's just like the ground neutralizes the electrical potential of the Earth. Because it may have potential to the moon. It may have a different voltage, an actual voltage, but it's a huge dampening effect because the Earth absorbs it and neutralizes it to ground. And if you hit it with enough, if you shoot enough voltage into the Earth, you might be able to raise the Earth's potential a little bit, its voltage a little bit, if you shoot a ton of lightning into it or something. But it just gets dampened. So yeah, of course there's no field inside in the sense that once all the electrons get to the same pressure, you're done. But it does take time for that to happen, and they're implying that this doesn't take time. Of course it takes time for that to happen, but obviously it happens fast, and especially little objects at the speed of light. It doesn't take very long for the pressure to equalize.
Static equilibrium is established.
Right. Equilibrium. That's the word they should have just stuck with. Oh, damn thing broke. I have to fix my smoker. Alright, we'll save that for later. Always something. Put these nice little magnetic switches in, but they're sort of a pain in the ass. These things stick to them. I mean, it's cooler than springs, but, I think springs would be more practical.
Therefore, a closed surface inside the conductor has no flux through it.
Right, because basically whatever hits the surface travels right through and blah, 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 blah. It conducts. It does exactly that. It behaves as a conductor. The pressure on one point will just neutralize.
So the net charge inside must be 0. But there can be charge at the surface, and no matter what's outside, the surface charge makes the field inside equal to 0.
Just saying that the interior is all conductor, therefore it's always going to be the same pressure. So no matter what happens, the interior is always going to be the same pressure.
And since all the action's at the surface, a metal box of any sort, even a flimsy screen-covered cage, can keep out an electric field.
So let's understand. It's not like all action is at the surface. It's just that surfaces are where the atoms are not as connected. So if there is going to be an imbalance somewhere, it's going to go to the surface, because the surface is where electrons are sort of free of the other electrons, more free. So they're the place that's going to show you, where there still can be an imbalance, because the electron doesn't have other electrons on both. If I only have one electron, that guy next to me, I don't have any that guy over there, obviously any pushing pressure, I'm just going to move, okay, because I don't have to worry about it. So I can move away from him, and I can have a different amount of pressure to the exterior world because I'm not connected to him. I mean, I'm not under any tension. So the surface, or where the tension, there has to be a mitigating electron that, has to be the last electron. He's still attracted to the proton, but, there's all this flexibility because he's not as bound.
That fact can be demonstrated with this device.
I don't think this actually demonstrates that fact. I think it demonstrates a different fact, regarding how the force is dependent on polarization and a lot of other things. That's what this experiment really demonstrates.
Electroscope. Notice how it responds to the field of an electric charge.
So this is just basic stuff. They're picking up the charge off the glass plate by putting his finger on. He's creating a ground, so the charge goes into the plate. So then he picks up the plate. It has the charge on it. Blah 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 blah.
Notice too that even when an electroscope's inside the cage, it reacts in the same fashion.
Right, but it's really not in the cage yet because you didn't close the cage.
However, when the box is enclosed, an electric field can't enter to disturb the globe.
All right, so it does enter. It just obviously doesn't enter complete, and that's sort of what this is illustrating. So if you make these holes big enough, okay, the charge will get through. So it's just the size that is the only thing that's inhibiting the progression of the charge, is just the size. And the size is basically destroying it's diluting the strength of the charge. And it's absorbing it entirely. It's sucking it in terms of pulling it through all these pieces of connected metal. So anything that hits the metal doesn't get through. So you just weakened the charge. You didn't destroy it.
Any metal box can do it. And to this day, any metal box that does do it is called a Faraday cage. Of course, not every Faraday cage was designed to protect its contents from electric fields.
Yes, and like I said, the only one that does it completely is if you make it out of sheet metal or something. Well, then you have a complete shield. But you can create enough of a shield by just having enough absorption to degrade the force enough so it can't affect the electrons. Not enough of it's hitting the electrons to cause the electric effect. So the pressure has to be caused by enough stuff hitting an electron to push it so it rebounds. And that's the effect of charge, is to fill something up so it can spread that effect. And you can't increase the pressure of the electrons unless you push them with a sufficient amount of energy. And the cage just prevents there from being a sufficient enough for each individual electron, because the cage is breaking is taking away enough of the energy. It's diluting it beyond the minimum amount needed. The density is too low.
The steel girders of a bridge or the scaffolding of a tunnel probably couldn't care less about keeping electric fields at bay. But they do a pretty effective job of it nonetheless. Why? Because radio waves are...
Right. Well, see, radio waves, it gets a little more complicated because they're polarization. So this is another one of these arguments where the individual electrons have to be hit by a more than one piece of energy, the frequency, between the cannonballs. And if it doesn't get hit by the complete frequency, that is, the cannonballs are coming slightly out of straight line. And so what the girders and things are doing is this cannonball gets through, but the second cannonball was a little bit off, and that one hit the girder. And so now the frequency is gone because one of the cannonballs necessary to seeing the frequency has been destroyed. So now it can't see. This frequency isn't the same as this frequency. So because your radio is not tuned to this, you won't hear what actually got to the antenna. What actually got to the antenna was disturbed by the fact that the metal blocked part of the signal. So part of the frequency was destroyed, which means the frequency isn't now a consistent row of cannonballs. You've broken the Morse code by taking some of the elements in the Morse code out. You can't read it anymore. The SOS doesn't, you can't send Morse code if some of the codes are missing, the bits.
A kind of disturbance in the electric field. And because whether it's a bridge, a tunnel, or merely the enclosed container that its name implies, a Faraday cage isn't a great place to get good reception.
So you can see that they're still getting reception even with this fine cage. And if they made the little cage holes bigger, they'd get even more reception. If they made them even bigger, they get more reception. So it just has to do with the size of the openings.
Outside again, the reception's fine. In any case, while cars can go just about anywhere, where can the lines of a uniform sphere of charge go?
They can go anywhere.
An extended region of charge might consist of many point charges in space.
So again, this is this radial thing. Understand, this is elemental to the whole thing. The whole thing is straight line radial force. That's what everything's made out of. That's how the whole system runs. Straight line force. Force isn't bent. Force isn't curved. Force isn't doing any of this stupid loop-de-doo stuff that they always draw. That's not what the force is doing. That's what an object in the force, depending on its polarization, will do. Very different what the effect is versus the cause. The cause is always this stuff. Straight line photon force.
But if it's symmetrical, the electric field has only one place to go, and that's outward. According to Gauss's law, the flux through...
And again, it's only going outward because it's reflecting. Okay, obviously. Again, if there was an external force, you can understand that it can only do three things. It can reflect, bounce off. It can be absorbed, kept as energy, and then cause it to move. Or it can be ejected in some other direction. The end. The three options. That's it. Nothing else can happen.
Through a closed...
It's a ball of momentum. What does the ball of momentum do? And in the case of magnetism, it always either reflects back where it came from, or it's deflected perpendicularly, depending on whether it's a positive force or negative force, whether it's north force or south force.
Surface outside depends only on the total charge. And if the charged region is a sphere, the size...
It always will end up going spherical if it's big enough. It's like the only reason why meteors aren't spheres is because meteors are made of big rocks hitting each other. So they started as spheres. And you can almost see it in the impacts, the ones that break apart, after they collided, and over time they get hit again and they break apart. And you can see the scar is perfectly round. So the objects were kind of already doing the rounding thing. But their shape would go spherical. They just don't quite have enough gravity to take material that's already in a condition, that is, it's already magnetized and stuck to each other. And there's just not enough gravity yet to smooth it over. But as soon as you make it big enough, it has to go spherical, because the gravitational force becomes stronger than the chemical bonds that are holding the atoms together, and it forces them to rearrange.
Makes no difference.
So, in other words, the electric field outside is the same, whether the charge is uniformly distributed in a sphere or concentrated at a point at the center.
Yes, the same light bulb will create the same amount of light. You can't change it if you're the same distance from the amount of photons. So making the light bulb bigger but duller doesn't change how much light you're going to get hit by.
And by the same reasoning, because it depends only on its inverse square nature.
So again, just think about it for a second. Just think that if their theory was right, that this thing is, this radial force was coming out. So just that one little point. It's a radial force, but you can clearly think that, oh yeah, but if that was an electron and that was creating this radial force, so that was a magnet, it was creating a radial force going out, well, wouldn't that push the bits out in all kinds of directions? So you can kind of understand that, no, it must be a force going in, because that's what's creating that round container. That's what's pushing it all together. I mean, it's just so obvious. You got to think in terms of an external push force. It's being pushed together.
The gravitational force of the Earth is the same as if all its mass were concentrated at the center.
Or all of its mass was concentrated on an interior lining. At any dimension, it doesn't matter. A very thick layer of lead and a big hollow center, and it would do the same exact thing on the outside. The outside wouldn't change a bit. So it doesn't need a center. The point is that there's a proportional amount of force from all directions, which automatically makes a sphere.
Isaac Newton had to use his most powerful mathematics to prove that point, which may have contributed to the 20-year...
See, I don't think he proved the point. What he did was discover it. So again, this is part of the part that's kind of funny. He didn't need the mathematics to discover the inverse square law. He needed the data that pointed to the inverse square law, and then he created a mathematics that allowed you to understand how it would affect different bodies in motion. So the complex part was explaining the effect of things that have momentum, things that have their own vector of energy. And now you're putting them in a field of energy, and you have to figure out, well, how's their vector going to combine with the new vector being created by the new forces that are affecting it. That's the complex mathematics, is figuring out the trajectory of the space shuttle. It's got a big flame, and so that's one piece of momentum, and it's got the gravity pushing down on it. Then it's got its own pointing vector, in the sense of which way is it pointing, when it's doing its momentum.
Delay in the publication of the Principia. But with the help of Michael Faraday's vivid mental picture, the reason behind the idea can be perceived and completely grasped without any mathematics whatsoever.
Right, so they didn't talk much about Maxwell here, but Maxwell is who screwed it all up. I mean, Maxwell had the same idea. Well, maybe they'll talk about Maxwell here.
Not that mathematics wouldn't apply. After all, in the end, the best scientific expression of Faraday's ideas, indeed the ultimate triumph of the electromagnetic field theory.
See, the ultimate triumph of the electromagnetic theory. No, it wasn't a triumph. It just combined what other people had done and recognized the fact that there's this huge relationship between magnetism and electricity. That's all that Maxwell did. But he committed a huge crime against it in the sense that he broke the two fields into two opposite forces and created fake constants of permutivity of space and permeability of space, which weren't even real constants, and those two constants had a proportional relationship to the speed of light. So all he did was establish, then by establishing that these forces were related to the speed of light, he ended up saying they're light, which means they have a frequency, when they don't. So a lot of mistakes made.
Would be the mathematical expression of James Clerk Maxwell. Faraday would come to admire Maxwell, and quite properly, the admiration would go both ways. Responding to a letter from Faraday, Maxwell wrote, "You are the first person in whom the idea of bodies acting at a distance has arisen as a principle to be actually believed in." Now,
yeah, simply understood as rays, like sunlight. Straight line rays. And so what do? They show this stupid animation where they have some source of gravity or some source of charge at some location over there off the screen to imply that there's all this curvy crap.
nothing is clearer than your descriptions. You seem to see the lines of force curving round obstacles.
Right, the lines of force curving, so that's Maxwell's way of describing them, and obviously when Faraday's talking about them, he's talking about lines, straight lines of force. So again, this word line of force and then lines of pressure or gradients of pressure, they should have had some other way to describe the three different ways you can use lines to illustrate effects. These lines have to do with things that have momentum and are moving. They're not lines showing what's the force at any one location.
Obstacles and driving plummet conductors, and swerving towards certain directions in crystals, and carrying with them everywhere the same amount of attractive power spread wider or denser as the lines widen or contract.
Right, so that's where he's talking about the lines widening and contracting. Yeah, the inverse square law.
And thinking of gravity as well as electricity, Maxwell concluded, your lines of force can weave a web across the sky and lead the stars in their courses.
And so Faraday had this idea about lines of force filling all of space. And there's no doubt whatsoever.
Right, and so everything's radiating what it's getting hit by. It's reflecting. Everything's reflecting something. And if you're moving, it means you didn't reflect it, you absorbed it and are now moving because of it, or you deflect it. So you either deflect it, reflect it, or if you absorb it, you use it, and then you can give it away. But that's it. It's always, the momentum never dies. The little bits of momentum are eternal. They came with the beginning of the universe, and they move everything that moves. Everything we call a thing is made up of those little protons and electrons, and those protons and electrons are getting hit by that force, and they're interacting with each other based on how they absorb and reflect, what they absorb and reflect.
Whatsoever that Faraday believed that those lines were really there. And that,
Right, and the rest of you kooks stop believing. And that was a huge mistake, because they are really there. They're made out of a real force, and the real force ends up being photons when it's at a frequency, and it's gravity when it's not at a frequency and not segregated for polarization. That is, it's mixed red and blue. And when you segregate it for a color, that is, you make more red or you make more blue, then you're charged. And when you smash two charges together, you end up with a magnet. The end. It's that simple.
and then along came James Clerk Maxwell, and he transmuted Faraday's idea into our modern view of the electric field. And once that was done,
Right, and the modern view breaks it all into pieces, creates this fake notion that there's some electric field and a magnetic field, like there's two different fields in the sense that electricity is different than magnetism, when no, there's two different fields in the sense that there's positive and negative fields. That's the two different fields. There are not an electric field and a magnetic field. It's always the same energy. It's either blue cannonballs or red cannonballs, and that's all there is.
Faraday's lines of force no longer existed. They were gone.
Which was a huge, stupid mistake, because they're obviously the mechanism. It's the same mechanism that creates gravity, same mechanism creates magnets, same mechanism creates electricity, and it just has to do with whether you're segregating for blue and red cannonballs or whether you're just taking any cannonball it hits. I mean, it's just such a stupid mistake.
And so a reasonable question you might ask is,
yes, she's hot.
why do we bother teaching you something we no longer believe to be true? Well, you might be...
And he's not.
...able to get some perspective on that question by considering something in today's science. We know, of
Well, obviously not that bad looking, but the glasses and the haircut,
course, that the nucleus of the atom is made up of smaller particles called protons and neutrons. We can smash...
No. Electrons and protons. Neutrons are just composites of electron and proton. So they're neutral in the sense that they have both charges. But they have a proton and an electron. So take the neutrons and just say, yeah, forget about it. They don't do much. I mean, they just provide a conduit. They just allow the protons to get closer to each other because they put an electron between them and allows all the energy to escape, and therefore you can create this, you can put two protons right next to each other if you put an electron right in between them, quite obviously. But the only game players are really the proton and the electron. They're the players, and the only players in the force are positive force and negative force. The end, done, finished, completed.
Smash the nucleus apart and get out the protons and neutrons and study them and so that we know they're real. But we also believe today that the protons and neutrons themselves are made up of even smaller inner constituents, which are called quarks.
Which is just crap. Totally unnecessary nonsense you don't need to play with. The real game is understanding positive charge and negative charge. Quarks don't let you understand any of that, so just forget about it. It's not interesting. It's useless crap. You have enough on your table right now. You don't need any new particles to screw up you're connecting the dot picture.
But it turns out that it's impossible to smash a proton apart and get out the individual quarks. The quarks are forever hidden inside of the protons and neutrons.
Right, but you still believe they exist. Why? Good question.
And so the question that arises is, in view of that, are quarks real? Well, that question is very similar to the question of whether Faraday's lines of force are real.
So now he's going to pretend that they had a good reason to forget Faraday's insight and pretend that it's something other than a straight line force, just like a light bulb. So instead of thinking about it as little rays or rays coming off the sun, instead of thinking about it sensibly as little bits of energy, little pieces of momentum moving through space, that's what the force is. That's why it moves stuff. It's because it has momentum, and it either gets absorbed. If I absorb the momentum, I move, or it reflects. Period. That's it. Oh gosh, this is so frustrating. How can intelligent people be so fucking stupid?
And in the long run, it may turn out to be irrelevant.
No, that's the important thing. So you just overlooked the most important fact. You threw it in the trash can for no good reason to focus on a bunch of quirky, stupid crap that doesn't have anything to do with the real game, which you already know is charge, 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 charge. It's all about charge. And what makes charge? Well, that makes charge is the fact that it's segregating. It's filtering. One thing reflects one kind of energy, one thing reflects the other kind. There, now you have all kinds of potential for wacky behavior.
Faraday's lines of force were a kind of mental scaffolding that had to be put up in order to build the final edifice, which was the electric field.
Right, which is virtual photon nonsense, totally non-descriptive, no causes whatsoever, no mechanism, no energy, no nothing. A vacuous explanation with nothing in it. Nothing. It provides no clue to a real cause. Oh, damn. All you needed to do was explain where the energy came from. Just look at the magnet and say, where does the energy come from? It clearly doesn't come from the magnet. The earth pushes me down. I fall towards it. Where does the energy come from? Obviously, the earth doesn't use any energy to make that happen. It doesn't burn anything. It doesn't have any, there's no smokestack. There's no steam engine. There's no nothing. Where does the energy come from? Damn it.
Now, of course, once the building is finished, the scaffolding isn't needed anymore, so it can be...
Right, and it's basically the cornerstone. So he threw away the cornerstone and the whole building falls down.
torn down and thrown away. But that makes it no less important because the building couldn't have been constructed without the scaffolding.
No, so it's just, this is bricks. You're putting them in the right place. Obviously, now you've decided. Faraday put the bricks in the right place. He was getting you right. He was squaring the thing. He was getting the weight right, getting it balanced, and now you've just unbalanced it. You've taken all the good work he did and trashed it, essentially.
Someday, looking back on our situation today, it may...
Yes, I don't know. I mean, someday, looking back on this, I don't know what the commentary is going to be. How the fuck could all you smart people accept an explanation that has no energy in it, uses terms like virtual thing, dark matter that's just obviously a contrivance? I mean, just so obviously saying the invisible man did it. It's like walking into court and actually saying to a judge or a jury, no, my client didn't do it, the invisible man did it. I mean, this is such terrible deduction. This is a horrible process. And the fact that all of you people just sit there and eat this garbage and say this garbage is a good enough explanation, this mush. And again, Faraday, a freaking 150 years ago, he sit there, he gave you 90% of it. It was right there in front of you to grab.
It may turn out that even the idea of quarks, which today's scientists certainly believe are real, turned out to be also just a kind of mental scaffolding.
Yeah, for what? For what? They're already amorphous, mushy bullshit. How can you even use them to build what? What are you going to build out of amorphous bullshit? Jesus. The only thing you can make is unicorns and pixies and gremlins. You're not going to make anything real out of that crap.
In any case, we'll get on with studying the final edifice of electric theory when we meet.
Right, like you actually have. We have an edifice. We have built a nice, straight, square building out of this physics. We have nice, rational explanations of causes and effects. You have nothing. You have bent space, no energy. Nothing. It's still just spooky action. You have virtual photon. Nothing. Doesn't explain why the photon is attractive or repulsive. It doesn't explain anything. Doesn't explain where the photon came from, who invented it, who used it, who made it, where did it come from. That's why you have to call it virtual, because you have no explanation for where the energy comes from. Because you know the photons have energy. You know they have momentum. So you just have to explain where the frig that came from. You have no explanation, so that's why you have to call it virtual. I mean, your edifice is paper thin. It's not even paper. It's used paper. Used in a certain dirty way. It's so bad. It is so bad that you're trying to sell this crap as an answer.
Here again next time.
So the rest of these are going to be awful tedious for me to watch. It's just going to be a horror. They'll just start talking about all their fake particles and all their fake interactions. Oh, it annihilates. Well, that doesn't mean it really annihilates. It just means it hides. Oh. So anyway, sorry, long video, but this is important. Because it really did get to the core of this thing. It pointed right at it. It points to you right to the fact that all the time they talk about these old guys, and they keep trying to imply that somehow they're supporting their nonsense in some way. No, they've clearly decided to take the game off the rails that Newton and Faraday created, and they're just taking the game right off the rails. They're off the track. They've left the rational building and just decided to make Fruit Loop physics. I should call it Fruit Loop physics. But anyway, thank you for your attention. That's all I can do. So, till the next time, long video. I gotta get to bed. Anyway, till the next time, and such.